Hello everyone, welcome to the next episode of my science podcast. Today I'm really pleased to be joined by Mr. Theodore Steele, who is a member of the Department of Applied Mathematics and Theoretical Physics at Cambridge University. He is researching relativity and gravitation, and in particular large-scale structure. So thank you so much for joining me today. I really appreciate your time.
Thanks.
So to begin with, may you tell us about your career so far and why you chose to go into theoretical physics?
So I'm kind of early in my career at the moment. I'm still relatively young, I like to tell myself. So I chose to go into theoretical physics kind of just because I found it interesting. That's actually quite a funny story. I originally wanted to become a biologist, and then while I was applying to university, I had a particularly fun, I always found physics interesting as well. And then I just learned some particularly interesting physics while I was writing my applications and decided to do that instead. And ended up becoming a theorist. And so I did my undergraduate degree at UCL, which is quite a good university in London. When you're doing your, I don't know how much you know about how academic career progression works already. Are you familiar with how undergrad, masters, and so on works? Okay, so when you're doing your undergrad degree in your final year, you'll do a dissertation where you'll usually do original research, but with a supervisor sort of helping you out. And I did quite a big research project at UCL with Professor Qinhua Wu, who's the head of theory at UCL has this rather funny and Byzantine organization where they have two different astrophysics departments that do actually broadly similar research, but are completely different to each other for historical reasons. And he's the head of theory at one of them. And I did a project with him on what's called the epoch of reionization. So that's a period very early in the universe. And this is the main reason I decided to go into cosmology. Originally, I didn't know if I wanted to do cosmology, which is the physics of the universe, or, particle physics or something. And I did a cosmology project with him, which was great. And that was when I decided to do that. And I was looking at, basically very early on in the universe's history, the universe was mostly filled with neutral hydrogen atoms, and then the first stars and things came into existence and began ionizing it all into protons and electrons with their radiation, and also ionizing helium into helium nuclei. And I was basically looking at how that works. I came up with my own methodology for a sort of applied maths technique for looking at how photoionized bubbles, as we call them, emerge and evolve around radiation emitting objects, including, I created a specialized version that was designed for Hawking radiation from black holes, which turned out not to be very good at irradiating anything. And then I went and did a master's at Edinburgh, where I did Edinburgh University, where I did where I was in the student at the Higgs Center Theoretical Physics. And I did another research project there on dark energy and modified gravity in a universe with sequestered vacuum energy. So basically, one of the big problems in theoretical physics is the fact that the universe seems to be expanding as though it had something we call a cosmological constant, but this is not in keeping with, but this is difficult to reconcile with particle physics. So if this is valid, we need to understand it much better. And a lot of people assume that the cosmological constant, while a good mathematical model, is not, for what we've observed so far, is not going to be useful in the future, and that we do need some other dark energy model to describe cosmic expansion. And a team in Nottingham, one of them was in Nottingham, and one of them, I think, was in, okay, I shouldn't have mentioned where they were from because I can't remember which universities they were both from. But a few scientists came up with this method for dealing with the problem, where they came up with a method which modifies the Einstein field equations and basically deals with the cosmological constant problem and allows you to then have a functioning universe without having to deal with that. So I was looking at how you can reconcile different dark energy and modified gravity models with that by incorporating it into what we call the effective field theory of dark energy and modified gravity. And then I came to Cambridge, and I now work in the large scale structure. So the basic idea of that is we have these things called cosmological probes, which are things we can observe in space, which tell us about other things, which we can, so, you know, if I want to know about how dark energy works, I can't look at it directly because it's not something I can, it's not something you can like look at in a particle accelerator or something. But what I can do is I can say if dark energy works this way or that way, it will affect the way galaxies interact with each other, and in such a way that the large scale distribution of galaxies will look a bit different. And then we can look at the large scale distribution, and then we can try to understand fundamental physics from that. And there are the two main cosmological probes really have been the cosmic microwave background, which has been a main object of study for a couple of decades. It was discovered in the 60s. Been a really major cosmological probe for about a few decades now, and is still under study. But also then, when that's the remnants of a really big pulse of radiation of light that was emitted very early in the universe's history and is still visible, you can still detect it. And you can basically use that. You can use that to see what the density of things was like very early in the universe's history, and you can also then study how the photons from this were affected by later time effects. But that's harder to do. And then you can also then look at the large scale distribution of galaxies, which is large scale structure, and that's what I'm doing. And that's much more the and that's there are a couple of really major large scale structure surveys coming out in the near future, which will hope, so Sphere X and LSST, for example, where they're doing really good measurements of a very large number of galaxies. So that should get good results. But what I'm doing is really just the theoretical work to come up with predictions for what they might see and what that could tell us.
Amazing. So before we go into large scale structure a little bit further, may you explain, I mean, you've already touched on this a little bit already, but can you explain the other areas of theoretical physics that you have either been working on or are in particularly interested in?
Well, I have quite broad interests, to be honest. I'm interested in almost every. I have a lot of interests. So if I explain to you every area of theoretical physics I'm interested in, I'll explain all of theoretical physics. So I mean, yeah, something I forgot to mention before when you had asked me about my career, and I was telling you, is I've also done some research on nuclear fusion. So, you know, fusion reactors. So basically the idea behind that was I thought I could maybe take some of the mathematical models we use in cosmology and apply them to the study of what plasma is like inside fusion reactors. And then it turned out not really. But by the time I realized that, I was already researching them. So I'm doing some research on the plasma dynamics inside fusion reactors as well. But yeah, so that's one area which is completely disconnected, which is quite interesting. And yeah, so I've done some research in the epoch of reionization. That's quite computational. I basically came up with this mathematical model which allowed you to look at how photons propagate around ionizing objects, ionize the atoms around them, and then take into account the recombination, which is where ionized particles become neutral particles again, and then calculate the ratio of ionized to neutral particles at every point around the objects. With the dark energy, with my dark energy research with sequestered vacuum energy, that was much more pen on paper theory, focusing on coming up with a modified version of the EFT of dark energy, which is basically, so yeah, incorporating dark energy and modified gravity into relativity basically, and then looking at how they work with sequestered vacuum energy, showed that some modified gravity models aren't compatible. But yeah, I mean, I have quite broad interests. So is there anything more specific you are hoping I would tell you about?
No, it's wonderful. That's absolutely fascinating. So you've told us what cosmological large-scale structure is. You've also told us what cosmic microwave background is. But how is large-scale structure better than cosmic microwave background?
Okay, so I mean, so the CMB still contains a lot of information and it's useful. And obviously I don't want to alienate any CMB researchers who might listen to this by saying LSS is way better. But it does have two big advantages over the CMB. So the CMB, when you look at it in the sky, you're basically looking up in the sky and seeing this microwave colored radiation. And you end up with a two-dimensional picture. And with LSS, you're looking at, you know, I can look up at the sky and I can see galaxies, and behind those I can see more galaxies, and behind those I can see more. So it's three-dimensional. So ultimately you can get a lot more information. If you want to study the correlation between, so basically you want to study the likelihood of finding two galaxies a particular distance away from each other. Well, it's three-dimensional, so you have a huge amount more galaxies you can sample. And another major advantage, so first of all, LSS offers more information, and you can get hypothetically, we can get higher precision results, but also late time effects, by which we mean cosmological effects that happened relatively late, you know, more recently, such as dark energy causing the universe to accelerate in its expansion, which has only been for the last few billion years, according to our current understanding. Well, the effect this has on the CMB will be very subleading and difficult to detect, because the light was emitted once way before this happened, and then if you want to look at late time effects, you're having to study very small effects it might have had on how the photons were propagating before reaching you. Whereas with LSS, you can, you know, large scale structures been there the whole time. It's been directly affected by it. Also, the further back the further away you look, the further back you're looking in history, because light travels at a finite speed. Light doesn't immediately reach you. If I shine a torch at you from the moon, it'll take a second for you to see the light. And so if you look at a galaxy that's, well, a billion light years away, you're looking at the universe at how the universe looked very long ago. So you can actually do studies where you're looking at, if I want to say, how did this dark energy model affect cosmological history? Well, I could actually model not just what it would make the universe look like now, but also what it would look like a billion years ago, 2 billion years ago, and I can then look at all of those I can look at them directly. So it's more information, and significantly better information when it comes to late time phenomena.
Amazing. So my next question is, how is the one loop bispectrum important in studying this?
Okay, so when you actually do these, when you actually have loads of galaxy observations, that's one thing, but then you start to think, well, okay, how can I actually learn from this about, so can you hear that? There's construction work going on next door.
I can, don't worry.
So you might then start to think, well, how can I actually get information out of this? How can I, you know, you don't want to come up with a simulation of the entire universe and where literally every galaxy would be, and then for a given dark energy model, and then compare it to what you see. So what you want to do is you want to come up with something that's statistical in nature. You want to say, if this model is, if inflation happened like this, if dark energy is like this, if neutrinos are like this, then on average we would expect the statistical distribution of galaxies to be like this. And so it's all, you're basically looking at statistical measures of the likelihoods of finding galaxies and things like that a certain distance apart from each other, and so on. And the mathematical objects we use to quantify these probabilities are called correlation functions. And for historic reasons that don't actually have anything, which I believe stem from engineering, the correlation function of the probability of finding two things in a certain configuration is called the power spectrum. And then expanding on from that, when you're looking at three things, it's called the bispectrum, and when you're looking at the correlator of four things, it's called the trispectrum, because you're correlating each one with three others, the trispectrum. And incidentally, this paper you are asking me about was on the bispectrum. We're in the act of publishing an immediate follow-up paper on the trispectrum today. I actually, before signing on with you, I got an email with a proof for the publication in the same journal. And so we're looking at these statistical objects, but then when it comes to, okay, so we can look at these statistical objects, but then we need to calculate roughly what these statistical objects would look like for a given, you know, model before we can compare it to observations. And this means solving some equations of motion that describe I'm getting ahead of myself. So basically, I'm telling you about galaxies, but actually our research is focused on dark matter density, because you can then, once you've done that, you can then map that to studying galaxies. We were just studying dark matter density. And so we basically have these equations of motion that describe dark matter density, and you can't solve these equations trivially. You can't just say, you can't solve an equation and then have an exact mathematical expression that will tell you exactly what the universe is going to look like. for a given, so we have what we call perturbation theory, where we come up with a where we come up with a not accurate but vaguely accurate description of what the universe would look like, and then add on extra layers which bring it closer to being accurate. And the one loop bispectrum is basically the first stage towards getting an accurate description of what the bispectrum would look like. It's where you're adding in a couple of layers of perturbation into each of your into your correlators, and so it's basically giving us a pretty high precision way of trying to measure the parameters of our fundamental physics. I mean, right now we've just done it for lambda CDM cosmology, so this is entirely if the universe evolves as it seems to evolve in a boring scenario where no dark energy model is correct, and neutrinos don't have any mass, and so on, then this is what the universe would look like. But then once we've finished this, which we have, that's why it's published, then we can start expanding on that and looking at how it differs in various scenarios with different fundamental physics, and then these can be compared to observations. And as I say, in the near future, there's already observational data available, but there are a couple of missions in the very near future, within the next 5 years or so, LSST and SphereX being probably the two main ones, among the two main ones. And the reason I mention them is because I've been in touch with the person who's in charge of SphereX, actually. And when we get the results from those, we can start using these theoretical predictions we're coming up with to actually hopefully place really high precision constraints on various fundamental parameters of physics, such as the equation of state of dark energy and things like that.
Amazing.
And the overall masses of neutrinos.
So this next question is quite a broad question. It's basically asking about the whole paper. But how did you go about presenting a detailed test and calibration of the matter bispectrum counterterms in the effective field theory of LSS against a suite of n-body simulations? And can you explain to our viewers what these terms mean first?
Okay, so when I was saying that we solve our equations of motion using a approximation called perturbation theory, that's not entirely accurate, because you have a lot of very complicated physical phenomena going on, which you can't just trivially model with some basic solutions to some equations. So we have very small scale. On small scales, you have gravitational collapse leading to dark matter halos and baryonic matter galaxies, and these affect this affects the distribution of matter, obviously, which affects the overall gravitational fields, which affects where matter on even larger scales is being pulled towards, feeling forces pulling it towards, which affects the large scale distribution. So even when we describe the universe using perturbation theory, that assumes that you can perturbatively describe the universe on all scales, which you can't do because these small scale effects can't be modeled perturbatively. They're completely chaotic and disconnected from the perturbation theory description of our fluid. So so there's a type of model in theoretical physics called an effective field theory, where if you want to describe something, but you can't completely accurately describe it, but you've got a model that describes it quite well on large scales, you basically come up with this model and then introduce a cutoff, which basically says this model doesn't apply below the cutoff on scales smaller than whatever size you decide is the smallest it can go down to. And then you introduce new terms which account for all of the effects that happen beyond that cutoff, and will then try and fit for those. And they're called counterterms. And so with the EFT of LSS, the effective field theory of large scale structure, we have perturbation theory, but we cut it off at a certain scale, which is quite a large scale, significantly larger than the distance between the size of a galaxy. And then we introduce counterterms, and which account for everything, all of the dynamics that occurs due to gravitational collapse on scales smaller than that, and accounts for how that will then affect larger scale structure. Then n-body simulations is just the fancy name for where you do a computer simulation that models. So this is all of our work is basically trying to come up with what we call an analytic model. So that's a set of equations that, and parameters that describes how everything works, so that we don't have to rely entirely upon doing thousands of computer simulations, which take quite a lot of time and effort to run. If I want to compare a dark energy model's parameters to what we see in large-scale structure, I don't want to have to run a trillion simulations on to tell me what the universe would look like and the statistical distribution of galaxies would look like with all of the different parameter settings. I would rather come up with a set of equations that allows me to come up with a prediction of that as a function of these parameters. But ultimately, in order to get the counter terms, we do still need to compare it to simulations. And so what we do is we run a simulation that models very accurately how the universe would evolve and what it would look like at any given time with lambda CDM cosmology. And then we fit our lambda CDM EFT of LSS model to that in order to get numerical values for our counter terms.
Fascinating. So why is the commonly used Einstein-de Sitter approximation for time dependence of the tree-level bispectrum insufficient for precise studies of the one-loop bispectrum?
Okay, so EDS means a matter-dominated universe. So if we pretend that the universe had only matter in it and didn't have dark energy, then it would be described as what we call an EDS universe, but it's not. It's dominated by the cosmological constant, and we model it using what we call LCDM. So EDS is not an accurate way of mathematically modeling what the universe looks like, but when you're doing perturbation theory in LSS, the EDS, if you treat the universe as being EDS, it's mathematically a lot simpler than if you treat it as being lambda CDM. And the amount by which and then you hope that actually the fact that it's a bit wrong can be accounted for with your counter terms, because your counter terms account for basically everything that's wrong with your model. That's basically what they're defined as being. Everything that's wrong with your model, they kind of correct for it. So you hope, well, maybe if we treat the universe as behaving differently to how it actually behaves, we can then correct for that with our counter terms as well. So people often use what's called the EDS approximation, where you actually do a sort of hybrid of treating the universe partly as though it was lambda CDM and partly as though it was EDS in order to simplify your equations. And then with for example, the one loop power spectrum, you do find that you can then absorb the difference between LCDM and EDS into your counter term calculations. Effectively, that means that your counter terms can correct for that, and you still end up with an okay description. But we showed that one of the things we showed in this paper was that if you do that with the one loop bispectrum, you actually do get inaccurate results. You can't simply magic away the difference. You do need to accurately describe it as lambda CDM, even though that does mean spending a bit more time crunching through the equations.
So almost to finish off with, what future work may come of this?
Okay, so immediate future work. I mean, right now I'm already collaborating on writing up a project on the two-loop bispectrum. So that's kind of the most obvious answer. Well, one-loop bispectrum, what follows on from that two-loop bispectrum? And I'm already, as I say, publishing the trispectrum paper, but this is all lambda CDM, including the two-loop one. So, I mean, immediate next steps will be to, first of all, as I said, we're looking at dark matter density fields. So we need to model how that then maps to dark matter halo distributions, and then from that to galaxy distributions, before we can actually connect it with observables, and then take into account distortion. When you look at things in redshift space, they're not always exactly as they seem. You get distortions called redshift space distortions, and most of these surveys are redshift space, or these surveys are redshift space, and so you need to take those into account. So, before our work can actually be compared to observational data, we do need to take into account what's called biasing, which is the fact that two different things which are related to each other won't always actually correspond exactly. So, dark matter distribution will obviously correspond to galaxy distribution because they both gravitate, but they won't actually correspond exactly. If you have an accurate description of where your density peaks of dark matter are, that doesn't mean you have an accurate description of where galaxies are. There's a little bit of difference, and that difference is biasing. And so we need to take into account density halo biasing to get accurate descriptions of where our dark matter halos are, not just density peaks in the density field, and then galaxy biasing between halos and galaxies, and then redshift space distortions So, I mean, there's quite a lot of work to be done before this can be directly compared to actual survey data. And then, I mean, well, this is all LCDM, like I said. So this is all basically all of our work so far has been setting the foundations for for having the infrastructure to place constraints on things. So obviously the next step, once we're able to compare to observations, will be to actually come up with modified versions of our model that account for different, non-zero neutrino masses and different dark energy parameters differently from just lambda and so on. And the most trivial way of doing that would be to play around with the equation of state of dark matter, which is an explicit term in our lambda CDM, in our growth factors, which we set to -1 for LCDM, but we can just play around with that. So that's probably the most straightforward follow-on paper when it comes to constraining parameters, but there are lots of other ways you can modify the model to study a lot of different physical effects.
Fascinating, wonderful. So that's all my questions answered, really. So unless you have anything else you'd like to talk about.
Do you have anything else you wanted to talk about?
No, it's wonderful. You've covered it all amazingly, and you've really explained it really well. It's completely fascinating. It's really interesting, and there's so many opportunities for the future to arise from it. So thank you so much for doing this. I really appreciate your time.
You're welcome. Oh, and something else I will say before I go is if you're interested in it, then obviously do a degree. Since you're first, I've heard that some people have put off doing degrees because they have to pay back the student loan afterwards, and there's this controversy about people in politics, people saying, oh, you shouldn't have a student loan, you should just get your degree for free. You do get your degree for free because you don't actually have to pay the student loan back unless you earn above a certain amount. So it's really just technically a additional income tax. So don't allow that to in any way. Anyone listening to this who's put off doing a degree because of the student loan, don't allow that to put you off at all. You should definitely do a degree in physics if you're interested. If you want to go into theoretical physics, then the most standard way of doing it would be to do a mathematics degree at Cambridge and then follow that on with a PhD here if you can. That would probably be the most sort of certain way of getting a good career in theoretical physics, but ultimately a degree from anywhere is good. All universities that do theoretical physics are good, so I would encourage you to keep going with it if you're interested.
Thank you so much. Thank you. Yeah, and thank you everyone for listening. So I'll see you next time.